Hello everyone, I'm Yu Shisun from HKUST. It's my pleasure to introduce our work, Record Related Tables Enhanced Column Semantic Type Annotation Framework. This is our outline. We'll introduce the background and motivation of this work first. Accurate column semantic type annotation is an important task for various downstream applications, such as schema matching, data cleaning, data integration, etc. However, there exist two main challenges: the difficulty of properly handling wide tables, and the difficulty of utilizing inter-table context information. The first challenge is that existing approaches cannot properly handle wide tables. For instance, Taby and Duoduo, the two state-of-the-art approaches, utilize BERT to encode the whole table content in order to perform column type annotation for each column. However, they are limited by the inherent BERT maximum input token length limit. As shown in the figure here, the tables can grow very wide. Encoding the table content for such tables become infeasible for these approaches. The second challenge is the difficulty of utilizing inter-table context information. Existing approaches ignore this piece of useful information. As shown in the figure below, the table on the left has very few rows. Thus, it is rather difficult for people to annotate the correct column type based on the scales information inside the table. While the table on the right is similar to the table on the left in terms of table content and schema, thus can become a useful supplement for the table on the left. By incorporating the context information across tables, the annotation of the column type in both tables are expected to be enhanced. However, utilizing such inter-table context is non-trivial, since we do not always have access to the table headers or table schema information in a data lake application scenario. How to effectively align the tables that are related is a challenge. In order to handle the challenge of incorporating inter-table context information, we propose a novel name entity schema. As shown in the figure here, the name entities of each column are extracted, and each column is represented by the most frequent name entity type. The name entity schema for a table is defined as the concatenation of the name entity type of each column. We can observe that the tables with the same or similar name entity schemata tend to be from the same or similar data sources, and thus are likely to be the constant complement for each other's. And therefore, they tend to have same or similar column semantic types. As shown in this example, table 1 and 2 have the same name entity schemata. And indeed, they are both describing the content of TV series. While the third table has different name entity schema, the third table is about video games. We notice that by encoding the related columns, as known as the inter-table context, instead of encoding the intra-table context, the wide tables can be naturally handled, since the sequence length required to encode the columns does not grow with the table width. We now move on to define some important concepts of this paper. We start with the important concepts defined in our paper. The first one is name entity schema, which is the table schema generated based on the most frequent name entity type extracted from each column. The details of the generation will be discussed in the methodology part. The second concept here is the related tables, which are the tables that share the same name entity schema and are similar in content with the original table. The third concept is the sub-related tables, which are the tables that share a similar name entity schema and are similar in content with the original table. The column semantic type annotation problem is defined as follows. Given a web table T from the dataset D, denote the target column as CT in T. The column semantic type annotation W annotates CT with the semantic type YT bar, such that YT bar best fits the semantics of CT. Now, we introduce the methodology used in our paper. This is the overview of our pipeline. The first step is to perform name entity tagging on the tables in the dataset. After obtaining the tagged name entity in each table column, we filter the table based on their content similarity. Then, based on the name entity schema generated, we perform table finding and alignment in order to identify the related tables and the sub-related tables for the target table. Next, each target table column together with the corresponding columns in the related tables and subrelated tables are encoded. Based on the embedding obtained, we perform table column annotation with the use of classification module. So the first step in the pipeline is name entity tagging. Given a table T, we use the spaCy tagging tool to identify the name entities in each column and tag them. We further notice that the type, dates, and person can be further divided based on the data format. We further include an additional empty type for the column if no name entity type is detected from the column. The most frequent name entity type in each column forms the name entity schema. The second step is table filtering. To filter out tables that are irrelevant in content, we compute the J-class similarity between the set of words for each table pair. Specifically, let AI and AJ denotes the set of words in table TI and TJ. We compute the J-class similarity as follows. And if the J-class similarity is greater than threshold, we include TJ as a candidate table of TI. Empirically, we set the threshold to 0.1. The next step is table finding and alignment. We consider the related tables and subrelated table to form the intertable context for the target table. Specifically, the related tables are identified as the candidate table TJ that share the same name entity schema as the target table TI, while the subrelated tables note that they are candidate tables that have similar yet not the same name entity schema with the target table. We consider the following two requirements, namely the schema similarity and column location alignment. Schema similarity is the requirement that the name entity schemata of the subrelated table and the target table should not be very different. To implement this, we compute the edit distance between their name entity schemata. If the edit distance is less than the threshold, then we regard them as schema similar. In our paper, we regard the schemata to be similar if the edit distance is less than or equal to the square root of the width of the target table. Column location alignment requires the name entity type of the target column matches with that of the column at the identical location in the subrelated table. This requirement is mainly for identifying the aligned intertable context column for the target column we aim at annotating. Then we introduce how to perform column encoding. We encode the target column, align columns in the related and the subrelated table separately with birds. The encoding of the target column is normal. The cells in the columns are concatenated, tokenized, and encoded by birds. Note that the maximum input length of bird is constrained to 512. We promote a fair allocation of the tokens to each aligned column in related table or subrelated table. For example, if the target column has 4 aligned columns in the related tables found, we allocate 512 divided by 4, which is 128 tokens to each aligned column during the encoding of related table context. The encoding of subrelated tables is similar to that of related tables. As a result, we obtain 3 embeddings, which are the embedding of the target table itself, the embedding of the related tables context, and the embedding of the subrelated tables context to annotate one single target column. The final step is classification. The embeddings of the target column, related tables, and subrelated tables are passed to 3 corresponding classification modules. Each classification module contains 2 layers, which are the dropout and linear. The generated output embeddings are combined with learnable weights, alpha, beta, and gamma. We then use the cross-entropy loss as the loss function to train the model. We now come to discuss the experimental details. We experiment on 2 datasets, the WebTables datasets and the SemTab 2019 dataset. We consider the 2 metrics, support-weighted F1 and macro-average F1 scores. The support-weighted F1 score is the weighted support of per-type F1 scores, while the macro-average F1 score is the average of per-type F1 scores. Thus, the later one emphasizing more on long-tail types. We perform 5-fold cross-validation on the 2 datasets. Here, we present the main experimental results. We compare Reka against the following baselines: Sherlock, Taybird, Taybi, and Dodo. We noticed that Reka outperforms all the baselines in terms of the two F1 scores on both datasets. Specifically, Reka boosts state-of-the-art performance by 4 and 7% on the SimTab 2019 dataset, while achieving a performance uplift of 0.9 and 5.5% on the WebTables datasets. We conducted an ablation study on Reka by considering the Reka target-only, Reka without related tables, and Reka without sub-related tables models. We noticed that the performance drops when the sub-related table context and related table contexts are removed. An interesting point is that the performance drops on macro average F1 scores are greater than that on support-weighted F1 scores. Incorporating eta table context can improve the annotation quality on less populated semantic types. We further conducted experiments to analyze the learning data utilization and input data utilization of Reka. For the learning data utilization experiment, we considered the different amount of label training data on both datasets. Reka still outperforms all the baselines when the amount of training data is reduced to 75%. The learning data utilization results show that Reka has the advantage of training a high-performance model with a relatively small amount of training data. For the input data utilization experiment, we consider changing the value of maximum sequence length limit. Annotating columns accurately with only a small number of tokens is a crucial factor in evaluating the performance and robustness of column type annotation models. We noticed that on the SimTab 2019 dataset, the performance of Reka dropped by only 0.2 and 1.8% when we reduced the max length to 256. On the WebTables dataset, Reka still outperforms all the baselines, even if we reduce the max length to 32. This phenomena demonstrates the robustness of Reka when dealing with data with small input size. We conducted a parameter sensitivity experiment over the important parameter, the Jacobs threshold. We observed that the performance is generally stable for the threshold in the range of 0 to 0.3. In practice, we suggest finding the optimal value of this threshold based on the dataset. Now, we summarize the paper. In summary, we propose Reka for column semantic type annotation. Reka extracts and leverages the intertable context to enhance the annotation quality of the target column, thus resolving the white table issue. We define a novel name entity schema for the Reka to efficiently align related and sub-related tables, which resolves the difficulty of incorporating eta table context. We conduct extensive experiments to show that Reka outperforms all the state-of-the-art. The result demonstrates the effectiveness of utilizing the intertable context to annotate column semantic types accurately. We show that Reka is data efficient and learning efficient since it requires shorter input token sequences and fewer training data to achieve high performance. Okay, this is the end of this presentation. Thank you for listening.